Hi folks, Vipin here. After a long time I've been making a video, and that's mostly because I've been quite busy in working with a lot of things related to my website. So this will be my first video when it comes to a science topic. So keep your fingers crossed. I hope you like the way I explain. I was a science student long time ago, 2003 to 2005. I did my pre-university in science. My combination was physics, chemistry, bio, and mathematics. I vaguely remember most of my knowledge, and I had really good teachers uh, who delivered the concepts in a very lovely way. So I'll be using most of my knowledge from them to explain a lot of topics in the future. Now, this particular video will be about solid state and the problems that was there in this particular unit. Now, I'll be just doing three problems that will take a certain amount of time. But nonetheless, before I start doing the problems, let me tell you why is it that you need to study solid state. Now, this is something which most people don't tell you. That is, why is it that you need to study something like this? A solid state, if you look at it on anything which is in fact made up of particles, now that includes everything. At the subatomic level, you need to understand why does a particle behave like this? Okay, why does a particle behave like this? Last week I came across a lovely video where they showed liquid magnets. Liquid magnets. Now that's really cool stuff. For a moment it looks a lot like black solution, and as soon as you put a piece of iron next to it, you can actually see the magnetic effect there. The iron in fact practically gets absorbed into the liquid magnet. Now there are a lot of practical uses for these things. I even came across substances which people regard as hydrophobic. Now, phobic or phobia here refers to fear. Now, they've actually developed substances wherein if you spray a hydrophobic gel, let's say on this board, if I were to throw a bucket of water on this board, the water would just simply slide off this particular uh, board. It doesn't really stick on anywhere, it doesn't really get attached anywhere, it doesn't cause damage anywhere. Now, all these different products have been possible because people have done a lot of research in solid state. They want to understand how molecules, atoms, are behaving at the subatomic level. And by understanding them, you will be able to get a better scope as to how you can develop new products and the way in which these products can actually behave at the subatomic level. Okay, now let's get started with some of the problems related to solid state. Now, I can't really tell you from what book I've taken these problems from because they are from uh, different textbooks from different universities. I'm not even sure which university I took this from. But nonetheless, here is the problem. I'll read out the problem, but nonetheless, I would have mentioned it in the description below. An element has a BCC structure. BCC here with a cell edge of 288 picometer. The density of the element is 7.2 grams 7.2 grams per meter cube. Okay, how many atoms are present in 208 grams of this element? Okay, how many atoms are present in 208 grams of this element? Now, what I noticed is when you're doing problems related to chemistry, you need to have an outstanding imagination as to how things work at the subatomic level. Now, I know I've said that word a lot. Believe me, if you really want to understand these topics, you must have a really good imagination. Now, firstly, let's look at the volume of the unit cell. Now, the volume of the unit cell here has been given as 288 picometer. Now, this comes a bit of a problem because when it comes to calculations, it's better off if you can convert it to centimeter. So this you need to convert to centimeter. Now, when you convert this to centimeter, you first take the root to meter. If you convert this to meter, it actually comes to 288 multiplied by 10 to the power of minus 12 meter. Now, you can do this if you have a good understanding of the various units used for measurement. Micro, milli, if you are familiar with them, you can actually go about deriving these different values here. Okay, and then convert this to centimeter, 288. Remember, this is meter cube. So multiply this by 10 to the power of minus 10 centimeter. I consider the cube factor here because I'm considering volume. Volume, remember, is a three-dimensional quality. Okay, it's a three-dimensional quality. When you use volume, let's say you refer to an engine of a vehicle, when you say 100 cc, 100 cc here is cubic centimeters, which is nothing but volume. Okay, so it's a three-dimensional quality. So you need to imagine this at the three-dimensional level. Now, this 2.38 multiplied by 10 to the power of minus 23 centimeter cube. Now, I'm able to do this because I use a scientific calculator. I strongly advise that you don't do this on paper. Or if you're good at Excel, go ahead and do it on Excel. Now, I have the volume of the unit cell. It was previously given to me in picometer. I've converted this to centimeter because it's easier to calculate. The next thing that I'm going to do is find the volume of 208 grams of this element. Okay, to calculate the volume, you use mass divided by density. Okay, and this gives you 208 divided by the density which I mentioned previously, 7.2 grams. Let's ignore the gram here, 7.2, and this should give you 28.88 centimeter cube. Okay, this is the volume of 208 grams of this unknown element that I mentioned. Now we need to find the number of atoms present in 208 grams of this. Okay, so how do you go about doing that? So to find the number of atoms, you consider the volume of 208 grams, the value which we arrived as 28.88, divided by the volume of every unit cell. Okay, the volume of every unit cell. So volume of every unit cell is 2.38 multiplied by 10 to the power of minus 23. And thanks to the magic of my Casio calculator, I am able to arrive at the value 12.08 multiplied by 10 to the power of 23 atoms. Now, this is an extremely long number. I can't imagine this number being present because this, to be very honest, the reason why we find these things very difficult to accept and imagine is because not many people would have told you this, but no one has really taken a picture of an atom or a picture of an subatomic particle like an electron or even a proton. We know the existence of an atom because of experiments and because of mathematical calculations. However, we don't have any photographic evidence to say that, okay, an atom looks so small. It's really, really hard to imagine so many atoms being present. Okay, now this is the answer that we've been looking for, and this is how we've arrived at. Okay, remember here they have considered a BCC type of structure. So for a BCC structure, this is what you would do in order to find out the number of atoms being present in this structure. Now, let me move on to another problem. I'm not sure what the rules are in your colleges when it comes to calculating problems related to chemistry, but I find it much more convenient if you're calculating them by using a scientific calculator. And I'm not sure if you can do any of these calculations using a simple calculator. I mean, how would you measure 10 to the power of minus 12 or minus 13 in a simple calculator? Anyway, let's move on to the second problem here. I'll quickly read out the question in the second problem. Silver crystallizes in a FCC lattice. FCC lattice, if the edge length of the cell is 4.07 multiplied by 10 to the power of minus 7 centimeter. So the edge length here has been given as 4.07 multiplied by 10 to the power of minus 8 centimeter. Now this is a really small number, okay? And the density has been given as 10.5 grams, 10.5 grams per centimeter cube. Find the atomic mass of silver. Find the atomic mass of silver. Atomic mass units represented as mu. We need to find the value of mu by using the data which has been mentioned here. You just need these two things and a little bit of the theory behind FCC types of crystal structures. Now, let me show you how you calculate this. Okay. In a FCC lattice, you have 4 atoms which are present here. 1, 2, 3, and 4. Okay. There are more here in these points, but we will not consider them. Put this as an atom, this as an atom, this as an atom, and this as an atom. Like I said, use your imagination and think of atoms being put in places like this. Okay. Now, so this should give you the value of Z. Z here refers to as the 4 atoms. That is the number of atoms present in the structure here, in the facing structure, 1, 2, 3, and 4. So I have 4 atoms being present here. Now, to find the atomic mass, all I need to do is M equals D Avogadro and Z. Okay, I will tell you how the A cube comes here in a moment. And now this is what I need to do. D has already been given, which is the density, which is 10.5 multiplied by the Avogadro constant, which is 6.023 multiplied by 10 to the power of 23, which in turn gets multiplied by 4.07 into 10 to the power of minus 8 the cube. I get cube here because the structure itself is a cube. So in fact, if you want to know what is the area of a cube, the face at least, this is what you would go about using. Okay, and then 10.05 multiplied by this, and yes, since I use a scientific calculator for all this, I am easily able to get the atomic mass of silver as 107.9 mu, or atomic mass units. So this is how you would calculate the atomic mass of silver. Okay, now let's move on to another one. Oh, before I move on, this is such an important factor in chemistry. Go to YouTube and search for periodic videos, and there is a professor by name Martin Polyakov. He explains the importance of this number, and after I saw the video, I was really amazed by how such a simple concept here has got so much of importance in the world of chemistry and in fact in the entire universe as well. So go to periodic videos on YouTube and you'll be able to get a very, very cool presentation on this particular concept. Now, the last problem which I would discuss here, a fairly lengthy one. Niobium crystallizes in a BCC lattice. So the crystal structure here is BCC. If the density is 8.55 grams per centimeter cube, 8.55, calculate the atomic radius of niobium using its atomic mass of 93. So nu here has been given as 93. Now in some textbooks you might come across the atomic mass of niobium as 92.9, but I would suggest you take it as 93 because it makes your calculations easier. Okay. Now the question here requires you to find the atomic radius of niobium. So how do you go about calculating this? Now, if you remember the previous formula that I used, m equals d, the Avogadro constant, a cube, divided by z. If I were to change the formula here and there, the first thing I would look for would be I would find out this. Before I proceed with my calculations, I first need to find out this. So I slightly change the formula and this becomes m and d multiplied by Avogadro's constant. So I'm going to use this and I'm going to find the edge length. Okay, so this is what I'm going to do now. I already have the data here. Z here is 2 because it's a BCC structure, and BCC the value of Z would be 2. 2 multiplied by 93. 93 would be the atomic mass of niobium divided by the density, which we looked at as 8.55, multiplied by Avogadro's constant. Okay, now this should give you the value as the edge length A should be equal to 3.304 multiplied by 10 to the power of minus 8. Once again, use a scientific calculator to calculate all this. Otherwise, it's impossible to do this on paper without screwing up majorly. Now, once I found out this, I can easily find the atomic radius. Okay, I can easily find the atomic radius. If you go back to the theory of BCC, you would see a formula wherein it shows A actually equals 4R divided by the cube root of 3. Okay, 4R divided by the cube root of 3. Now all I need to do is again substitute the values here and interchange the formula a little bit, and this is what I would be arriving at. So the value of A is something that we already know. So here R would be nothing but this is what I would be doing, 3.304 multiplied by 10 to the power of minus 8 multiplied by the cube root of 3 divided by 4. Now this should give you the atomic radius. R should be equal to 1.430 multiplied by 10 to the power of minus 8 centimeter. So you have an atom which has a radius of this particular dimension. I challenge you to imagine something like this. Now these are some of the problems that have been there in solid state. If you want me to work out more problems in this particular unit, let me know and I'll gladly do it. So far so good. I hope you found this video helpful. If you liked it, share it with your friends and do subscribe to my videos as well. Thank you for your time. Have a nice day.